Okay, so we are looking at logic as a medium for programming or as a programming language, and we call this process logic programming. Okay. And anything that we can do in any other programming language can also be done using logic as a programming language essentially. In the last class, we saw that we can define addition by saying, and we are writing this in Prolog style, that if you have 0 added to any number, you get the same number. So, this is an axiom essentially, and if you read it as a logic statement, you should read it for all x 0 plus x equal to x is equal to. And then we have the recursive clause, which says I should really put question mark here, because these are all variables. This basically says that if n plus m is equal to r, then n plus 1 plus m is equal to r plus 1 essentially, which is both are true statements. So, both are essentially true statements. Logic is concerned with true statements, but what Kowalski and Kolminow and other people showed was that by writing these true statements in an appropriate fashion, you can actually write programs essentially. And we saw that these two statements that we have here is a program for adding two numbers essentially. As a small exercise, you can, having defined plus, I would like you to define multiplication essentially. So, in fact, this has been known for more than a couple of centuries, that you can define addition in this fashion, and then you can define multiplication as repeated addition essentially. And then we saw that if we have a goal, like, let me use numbers here. That is this statement true, plus 3, 5, r. So, the question we are asking is this true, because we are saying it is a goal essentially. And then through a process of backward chaining, we saw that we could reduce this goal. So, we will keep these goals in what we will call as a goal set. And essentially, we will try to reduce each of these goals essentially, and we will stop empty. It means, if you do not have any more goals to solve, then you have shown that whatever you wanted to show. In our case, we have only one goal, and we put that in the goal set, and we are trying to show that this formula plus 3, 5 and a variable whether this how can this formula become true essentially, and we have seen that through a process of backward chaining we will reduce it to a different goal, which is 2 5 R 1, where R is equal to successor of R 1. And this in turn we will reduce to plus 1 5 R 2, where R 2 is again, or we can also write it as follows, where R 2 is equal to R 1 minus 1 essentially, or in other words R 1 is the successor of R 2 essentially. And then we reduce it to a goal plus 0 5 R 3, where again R 2 is equal to successor of R 3. I am not writing the question marks there, but at this place we do not need to reduce it to a sub goal essentially, because this matches of what we can call as a fact, which is that plus 0 anything is anything. So, all we have to do is that if you say R 3 is equal to 5, then this is true essentially, if R 3 equal to 5. So, once we know that R 3 is equal to 5 is true, we know that R 2 is equal to 6, and once we know that R 1 is equal to 7, and therefore, we know that R is equal to 8. Simply through a process of substitution, we know that this formula is true, the last formula in this sequence, if R 3 were to match with 5, which means its successor R 2 must match 6, and whose successor R 1 must match 7, and whose successor R must match 8, and the original formula is true if R matches 8 essentially, and we can return the answer yes, this statement is true provided R is equal to 8. And in other words, what we have done is we have added two numbers 3 plus 5 to give us R essentially. So, this is basically showing that addition has a logical foundation essentially. In practice, you can imagine that we are not going to do addition like this, because it is a very painstaking process, and you can see that the complexity, the number of recursive calls you have to make is proportional to the size of the first number that you are trying to add. So, which means that if you wanted to add 1000 plus 20, you would end up making 1000 calls to this program before you got the sum. And obviously, we do not think of addition as such a complicated process, and in practice even a Prolog program will not do addition like this, but this is just to show that logically we know how to add two numbers. So, let us do some more arithmetic. And let us look at this sequence called Fibonacci numbers. So, you must be familiar with this sequence. You start with 1, then 1, then you keep adding the last two numbers to give you the next number. So, 2 and 1 plus 2 is 3, and 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, and so on essentially. So, such a sequence is called, as you know, a Fibonacci sequence, and it is fairly straightforward to translate the definition of Fibonacci numbers into a program to compute Fibonacci numbers. So, a simple program, as you can imagine, would be as follows, that we define that, let us say this is the this thing, let us say 0 is the index of the number and 1 is the value of the number. So, the 0th number, or if you want to say first number, it does not really matter, is 1, then the next number is also 1, because we start with these two numbers. The rest is defined recursively, and I am sure you can write this quite easily now. So, successor of n so what is n here? N means we want the nth Fibonacci number essentially. In fact, we want n plus second Fibonacci number in this case, because it is the successor of n will be true if we know the nth Fibonacci number. Sorry, I should have is the R the result if I know the previous Fibonacci number or the one 2 before. If the Fibonacci number, the nth Fibonacci number is, let us say x, and the next Fibonacci number, n plus first Fibonacci number is y, and now we can use our program to add two numbers x, y, r. Observe that this is an AND sign here, but in Prolog style we are putting a comma, but essentially if you want to read this as a logical statement, you want to say that for all x, for all y, for all r, and for all n, even n is a variable, for all x, for all y, for all r, and for all n, if Fibonacci, the nth Fibonacci number is x and the n plus first Fibonacci number is y, and if x plus y is r, then the n plus second Fibonacci number is r essentially. So, that is what we are saying, and it is a definition of a Fibonacci number. So, if we wanted to solve, for example, a goal that calculate, for example, the 10th Fibonacci number, we would state it as follows. So, I will just write 10 here, and I take it that you will understand that basically there are 10 s's in a row followed by 0 is r. So, if that is my goal, then we had seen in the last class that we end up exploring a tree which is called a goal tree, which means that to show that this is true, I will have to show 3 facts which are the body of the above rule. So, either I can match it with the first statement or the second statement or the third statement, and we have already mentioned that Prolog will try this in the order in which you write them essentially. Now, obviously, this goal Fibonacci 10, the 10th number will not match the first statement, because that is talking of the 0th Fibonacci number. It will not match the second statement, which is talking about the first Fibonacci number. So, it will match the this one with a value that n is equal to 8 essentially, right, because when n is equal to 8, successor of 8 is 9 and successor of 9 is 10. So, we are talking about the number 10. Now, we will break this down into the 3 sub goals which are the body of this particular rule, which is that fib 8 x, fib 9 y plus 8 sorry and this is a, as we had mentioned earlier, it is an AND node in the sense that you have to follow all three this thing. We will also follow this notation that I just introduced, that we will write this as a goal set, which will say this Fibonacci for 8, I am not filling in the details, Fibonacci for 9 and this plus of x and y or. So, 3 goals we will put into a goal set, and again Prolog will take the first one, which amounts to doing a depth first search on this goal tree that we are constructing here essentially. How will this go? The to show this, let me just let us start as Prolog would do it, is it would now break up this goal. It will try to show this first, it will try to match it with the first statement, but it will not match because the first statement is talking about the 0th number, it will not match the second one, likewise it will match the third one, and we will have what you can see is a recursive call for Fibonacci 6. Let us use some variable x1 here, Fibonacci 7, x2 let me call it, does not matter, some variable name, plus x1, x2, some x3. And then it will do this 3 places, it will do this in 3 places, it will do this in 3 places, likewise it is going to do this one. The right hand side is the simplest because it has, as we have seen, a linear structure. We will keep reducing x. So, x plus y is r x minus 1 plus y is r minus 1, x minus 2 plus y is r minus 2, and so on and so forth. So, let me just put in 1 or 2 more here. So, this one for example, this is talking about the 7th number, and this is talking about the 8th number, and this is of course plus. Now, the point is, as you can see, there is a lot of wasted work going on here, that you are trying to show that Fibonacci, what is the 7th Fibonacci, you are trying to compute, in other words, what is the 7th Fibonacci number here as well as here, and likewise you are trying to compute the 8th Fibonacci number here as well as here, and there is a lot of repetition going on here essentially, and this one grows exponentially. Every node has 3 children, and you will have to, as you can see, go at least 10 level downs essentially. Of course, some of them will taper off essentially. So, when 6 will reduce to 4 as its leftmost child, which will reduce to 2 as its leftmost child, which will reduce to 0 as its leftmost child, but that will terminate because it will match the clause essentially. At some point it will terminate, but it is a big tree and it computes, does a lot of unnecessary computation. So, what we are trying to show is that even though you are thinking of logic as a programming language, and you have a straightforward way of translating a definition like Fibonacci numbers into a program, it does not make sense to do that because computationally that is very inefficient. So, let us look at how we can do it better. So, we will think of the statements both as logic as well as programs essentially. So, here is an alternative way of doing things, that, and this is a practice which we often do in many programming languages is that we introduce new variables and try to convert some of these recursive programs into iterative programs essentially. So, let us call this as a function f or predicate f rather, which is talking about this, and we introduce two values 1 0 and the result r here. So, an auxiliary program we are writing by adding new variables. We saw this, we did this when we were looking at unification algorithm also. We had an auxiliary program where the substitution was being built up essentially. And this auxiliary function, the base clause is that when you are talking about the 0th number, then whatever is the value here and whatever is the value here must be the value here. So, we are going to recurse on n as before, and this when n becomes 0, this particular thing will hold essentially. Otherwise, if you are looking at the n plus first Fibonacci number, okay. So, essentially just to give you an intuition behind what is happening here is that we start with this two pair of numbers 1 and 0, and then we keep adding them and keep. So, we add y plus z to give v, and then we bring this v here and we bring the larger of the two numbers here. So, we are shifting them essentially. Let us do an example and that will make things clear. So, let us say I am doing Fibonacci of 6 and I make a call with 1 0 and r. So, I will match this with this and move to the right hand side. So, ignore that plus kind, we assume that you do the plus essentially. So, what is plus going to do? 1 plus 0 is equal to 1, it will give us. So, value of v will be 1. So, we will get as a next level Fibonacci of 5. Now, 1 will come here, 1 will come here and r will remain there. Again we call the same rule, we will go to Fibonacci 4. So, 1 plus 1 2 will come here, 1 will move here and r will come here. Then we will call it with 3. Now, 2 plus 1 3 will come here and the larger of those two numbers 2 will remain here, and that is the result that we are looking for. Then we will go to the call with 2. So, 3 plus 2 is 5 will come here and the larger of them will go there. Five plus 3 8 and 5 will come here. Eight plus 5 13 8 will come here, R will come here. But at this stage, this one we will not need to recurse any more, because this will match this clause and we will get R is equal to 13. So, as long as the argument was positive 6, 5, 4, 3, 2, 1, we made a recursive call and we reduced it to a smaller problem. The moment it became 0, we had the result stored in the variable R directly and we can return the value R essentially. Now, you can see that first of all this is linear, as opposed to exponential essentially. So, if you are using logic as a programming language, we still need to worry about writing the clauses quite efficiently essentially. Now, Prolog is an implementation of logic programming. It is one implementation of logic programming, it does not have to be this thing essentially. What Prolog does, as we have said, is searches the goal tree in a depth first fashion. Which translates to saying that looks at statements in lexical order and looks at sub goals left to right. So, the order in which you write matters essentially. It critically influences the way that the program will work essentially. So, obviously, one thing that we have seen that base clauses first essentially when you are doing recursion, because every time it is trying to prove a goal, it must first try the base clause and then it must move to the recursive clause. If you write them in a different order, then they would do things differently essentially. So, the thing is that order matters essentially. Now, in logic programming, in pure logic programming, one assumes a non-deterministic machine essentially. So, Kowalski's idea was the following. That a program is equal to logic plus control. Now, this control in Prolog, it is depth first search. We already stated that Prolog looks at things in depth first search fashion essentially. But ideally, this control would be non-deterministic essentially in pure logic programming. What Kowalski wanted to work towards, what is this ideal? The ideal is that a user need only state the logic part. The rest should be left to the machine, and when you say a machine, we mean the inference engine and so on essentially. But that is only in the ideal cases, because in the pure logic programming, you do not worry about in what order you write things, because you treat all the set of statements as a set essentially, and the inference engine somehow picks the right things and does things for you. Whereas, in practice, when you use a language like Prolog, you have to write things in a specific order. So, let us look at an example. So, we had said that Prolog works top to down and left to right. Let us look at this left to right portion. Let us look at an example. Supposing you are trying to define a predicate called American cousin. And you define it as follows, that x. So, the meaning of this is that y is an American cousin of x, provided two things. One is that y is a cousin of x, and the second thing is that y is American essentially. So, there are two sub goals that you are looking at. So, supposing you write it like this. What is this program? What will this do? That if I have to ask the question, let us say goal, American cousin John X, let us say x 1. So, we are asking, does John have an American cousin essentially? What will this particular Prolog do? It will say, it will break it down into a goal set. So, starting with this goal set, we will reduce it to this goal set, American y and cousin What is this saying? Find an American and check whether she or he is a cousin of John. And let us say your program has access to the entire database of the US or of the entire world for that matter. And you can see that what this is going to do is, for every person which it can know to be an American, it will ask the sub query, the second query, that is that person a cousin of John essentially. Now, obviously, this is a grossly inefficient way of doing things essentially. Instead, if we had written the code like this, what is this saying? Find a cousin of John, assuming the same goal, and test whether she or he is American. And as you can see, because you expect John to have a very small number of cousins, let us say whatever 5, 10, 15, 20 or something like that, not in millions essentially. So, all you would do is you would test for those 15, 20 people and see whether any of them is American, and if any of them happens to be American, you would return yes, so and so is an American cousin of John. Otherwise, you would return no, saying no, John does not have any American cousin. Whereas, the first program would have looked at all Americans before saying that no, John does not have an American cousin essentially, if none of them happen to be a cousin of John essentially. So, obviously, the first one is much more inefficient than the second one. So, all that we have done is that logically we have not changed the definition. We have said that an American cousin means that you must be American and you must be a cousin essentially. But which one of those two statements you make first matters much more in Prolog essentially. So, I will stop here, and in the next class we will explore this idea of writing things in the correct order much more essentially.